Thank you, Ajit. Good morning, good afternoon, good evening, everybody. Today, we would like to introduce you with our new release of MSC Apex, that's Grizzly. We have come a long way in our Apex journey. We started introducing CAD-to-Mesh tool in early 2014, and you all have seen the power of modeler. In particular, we have been using modeler for creating the mid-surface modeling of most complex geometries. As the modeler became more mature, we started introducing Apex as a system to provide you with simulation capabilities. We have introduced linear static analysis, normal Morse analysis, linear dynamic analysis beginning 2015-2016 timeframe. Today, we are going to introduce additional simulation capability in Grizzly. We continue our journey to make sure Apex will be an extensible and a fully integrated platform for the future of CAE. Having said that, where are we in our journey? In Grizzly today, we are introducing the new simulation capabilities, that is linear buckling. In addition to the linear statics and linear dynamics, with linear buckling, now you can calculate the margin of safety against stress and stability of the section. We continue to enhance the modeling and meshing capabilities as we go along in each of the releases. What do we have in Grizzly? We are introducing linear buckling simulation, as I mentioned. In addition to that, there will be an all-new multi-sweep, multi-cut hex meshing capability, custom defeaturing, and results exploration capabilities where you can look at the cross-section forces and connection forces. And we also have quite a bit of enhancements in the existing capabilities of Apex, such as tie connections, macro record replay, section view, and quite a bit of usability enhancements. So with a lot of these new capabilities in Grizzly and with the enhancement to the existing capabilities of Apex, we believe today we can handle the large welded structures or large fabricated structures such as ship hulls, cranes, heavy machinery, etc. With that, let's take a look at quick demos of many of these features. The first demo is going to be how we can create the hex mesh in Grizzly. We have introduced what is called splitting of solids that helps to create the hex mesh in the previous releases with the hard split of the geometries. But during the hard split, we could create a hex mesh, but it was not contiguous across the boundaries. And now in Grizzly, we are introducing a new concept of what is called partitioning the solids in the form of cells so that when we create the hex mesh, there is a contiguity across the mesh between the cells. Yet it is still a single body. And not to mention that all other generated capabilities of Apex will continue to be available even in these hex mesh models. Let's take a quick look at the demo. Here is one of the gear models that we would like to create a hex mesh. And the first thing is to split the solids. I'm going to use the tool. And in order to split the solids, we could use any of the geometry creation capabilities that's available in Apex. Also, you can create some of the reference geometry to split the solids. Let's go ahead and create what is called some filler surfaces in this case. That's one reference split plane. Likewise, I would like to create one more. These are the two planes using which I would like to cut the geometry. Let's use the splitting tool And the user experience remains identical whether you are hard splitting a geometry or you are creating a virtual solid. Let's try both of them. And this is traditional hard splitting of the geometry. Which broke the solids into two solids, as you can see in the model browser as well as in the viewport. Now let's switch to partitioning of the solid. Not split that yet. Split, partition, select. That's correct. Okay, head surface. Now, as you can see here, the difference between the partitioning and splitting, when you do this partition, you can see the dotted line implying the solids is split, but they are contiguous, whereas here it is a hard split. Now, how do I know that these solids are hex meshable? When I click on this tool, if the solid bodies are turned into green, that implies that it is hex meshable. If it is red, then you can continue to split the geometry until those bodies become green, and then you can hex mesh. But right now, if you hex mesh it, you will get two different meshes that may not be congruent across split plane. How do you merge this one? You could use our Boolean tool to merge these split solids, consisting of some of them are virtual split and the hard split. Now you can see all of them become one solid, and now this is still hex meshable. We can go ahead and mesh this one with 2.5D hex mesh. Let's make a 4 millimeter element size and go ahead and mesh this. Now, as you see, it created a beautiful 2.5D hex mesh, and you can see it is contiguous across the boundary, and it is single body and single mesh. While we are here, do we have the additional capabilities where we can refine the mesh in the area of interest? For example, here, we could continue to use the other tools, such as we can refine the mesh by additional seeding of this edge. For example, I'm going to seed this edge to add 2 rows of elements. And let's say if I would like to make maybe 3 rows at the bottom face here, you can do so. Now, if you see here, we got the refinement of the mesh in the local area. So now we got the mesh done, and now we can get to the simulation, and either we could do a symmetry boundary condition, or we could mirror the model to get a complete 360 degrees. But while we are here, now can we take the power of Apex to do some geometry operations so that we can see the generative behavior of the mesh updates? For example, if I go to the push-pull, can we reduce the diameter of this pole, for example, from 12.5 to 9, let's say? When we do that one, the geometry got updated, and simultaneously the mesh got regenerated. Can we reduce the height of this pedestal? For example, now we could use the push-pull tool to update the geometry and hence updating the mesh. So you can do any of such operations on this geometry so that you can get a modified design of the geometry, and you can continue to do the simulation. For example, if I would like to reduce the height of this gear, and you can do so. So all the capabilities of the push-pull can be done on the solid to regenerate the desired shape of the geometry. So that's the power of Apex. Now, can we just go ahead and complete this one by mirroring this geometry? Let's say I would like to mirror, copy, so see, now we got the full 360-degree model, but however, it still has two solids and two mesh bodies, and we can continue to go and do the Boolean of these two bodies. And now it became one solid, and we can complete the hex mesh of this one solid. So that's the power of hex mesh using the multi-cut, multi-sweep capabilities of Grizzly. All right, what's next? Now let's take a look at what we have in Grizzly, what is called section forces. See, in any engineering simulation, once the analysis is done, the analyst would like to see what is the cross-section forces in any cross-sections, whether the size and the shape of the geometry is okay, or whether the load path is optimal. And how do you do that one? Today, you can do that one by cutting a cross-section to the model. Unlike the other preprocessor way, you may have to align the nodes along the cutting plane. In Grizzly, it doesn't matter. You can arbitrarily create a plane however you want it, and you can cut the model, and the rest Apex will take care of it. And you can cut the model whether it can pass through solid elements, shell elements, 1D elements, or even through some connectors. And along the cut plane, not only will be looking at the total cross-section force, you can also see the contribution of the different parts that is giving to that total cross-section force. Let's take a look at that. Okay. Right. Here in model, let's see how elegantly we can create a cross-section, then take a look at the cross-section forces. I'm going to quickly mesh this model, which may be 25 millimeter element size. And once the mesh is done, it's not that you need to create the mesh before you can cut the plane. You can cut the plane even on the geometry, and then you can mesh it, and we take advantage of the generated behavior. Let's see how we can cut the cross-sections. You can simply select the parts to be cut and select the location where you would like to define a cutting plane. That's it. And once we do, the rest will be done by Apex to calculate the section forces. Whereas while you are here, you also have the ability to reposition where you would like to have the cross-section, or if you would like to rotate that cross-section to any desired orientation, you can do so. It is as simple as that, defining the cross-section in Grizzly. Let's take a look at the results exploration of this cross-section. The same model was subject to some kind of a vertical load at the tip of the wing and constrained here. And we are looking at a typical stress plot for a vertical load of the cantilever behavior of the wing. Now let's take a look at the section forces. This model has two cross-sections that was created. Now let's take a look at the resultant section forces. When you go to that one, it'll quickly show you at those cross-sections what is the cross-section forces. Now, if you click on that one, it will give you what is the force to the cross-section. What are the other capabilities that we have in exploring the results? Now, you can look at the data through discrete, meaning that what are the contribution of all the elements that cuts through the cross section, and that's how it looks when you assign the vectors. And now you can look at, for example, if you draw a box around those things, it will show you the cross-section forces of the contribution of all those cut elements along the cutting plane. And you can also look at the different components, for example, X component, Y, Z, XY, etc. And all these things you can look at either in the local coordinate system of the cutting plane or global. And you can also look at, for example, I would like to look at the Z component plus the shear component of that one. Now you can toggle the two together, and now if you click on that, you can see both the components at each of those locations. So it is that easy to explore the result quantity of a cross-section forces in any of the simulation model. It is that simple to create a cross-section, and it is that simple to explore all the different quantities of results along the cut cross-section. Let's go to the next feature of Grizzly. In Grizzly, we are introducing what is called the linear buckling analysis. And setting up a linear buckling analysis in Grizzly is as simple as setting the context in the model. It could be a component, it could be an assembly, or it could be an entire model. And all the capabilities of FX, such as direct modeling, generative behavior, and connectors for assembly, all those things continue to work the way it does given in linear buckling simulation. Plus, in linear buckling analysis, we're also giving you the load events. That means the multiple loads can be applied, and you can look at the buckling behavior for each of those loads individually. Let's take a look at that. The same model for the same loading condition, I ran the buckling simulation. Let's take a look at the results exploration. When you enter the post-processing tool or the results exploration tool in Apex, now it's as simple as navigating through to look at what are the different buckling behavior under this load condition. For example, this is the first buckling mode. Now you can kind of pass through different modes that this model is subject to. And let's say you can look at this mode number 7. And as you can see here, it appears that most of the skin between those ribs seems to be buckling under this load. And now how do we know what is this load and what is the critical buckling? Clicking on this tool will take you through this what is called buckling table. And here, the red implies that under the given loading criteria, all these modes tend to be buckling. And now, if you change the load factor, change factor of the load, for example, in this case, I'm going to make it as 0.8. What that implies, at 80% of the applied load, the first two buckling is going to happen, and all the others seems to be okay. So by doing this one, you can critically look at what is the critical buckling load of particular mode and whether it is safe or not, or at what load it's going to buckle, and can I make a sensible design changes to make the design safe against buckling. And once we look at this buckling, what is important is that if I can go and refine the mesh in some areas, and can I do that one? For example, here, and if I would like to remesh some local area where the first buckling mode was, and then can refine the mesh and continue to update the model and rerun the simulation. How quickly we can do those things? I can go to the mesh tool and I can make this mesh, for example, finer mesh and pick that phase. Now you can see that local area of the buckling model has been modified with the refined mesh. And all the generated behavior, for example, if that panel was connected to the rest of the model and all those connectivity, in this case through glue, got updated. Now it is as simple as setting the context again and run through this buckling. That's how it is easy to set up the buckling in Grizzly and also to explore the results in Grizzly. And the next tool that what we are introducing in Grizzly is what is called custom defeaturing. And what is this? In previous releases of Apex, we have introduced the defeaturing of our standard features such as fillet, hole, chamfer, etc. But in any engineering design, there will always be some non-standard features such as sheet metal tabs, slots, and arbitrary shaped holes, what is called the keyholes in most of the shipbuilding industry. Now, how can we defeature these things? We have introduced a tool called pattern recognition, and one can recognize the pattern, and based on that one, and we can defeature. And not only that, that is available only for the non-standard features, it is also available for the regular features. That means you can take advantage of custom defeaturing to defeature many of these things. Let's see how it works. So here is an assembly of a kind of a shipyard crane, and now it has a lot of complex geometries. Let's take a look at this one of this model. And here, if I show the details of the model, there are quite a bit of geometry, has different shapes and different features. And how could we defeature all these things using the pattern recognition? Let's take a look at that one, the process. And the first step in this one, I'm going to get the mid-surface geometry of all these sheet metal components, which is easy, using the constant thickness option. And once that is done, now we can defeature that one on the mid-surface geometry. Okay. So how does it work? Basically, under the defeature tool, we have introduced what is called pattern recognition. In that pattern recognition, you also have certain tolerances. That means over the length of that pattern, then you also identify with a tolerance of 80% and also with a tolerance of 10 degrees. That means the shapes need not be exact, and it can be with an option of introducing this length and angle tolerances. Now let's pick one of the pattern. In this case, it is a rectangular notch. And once you identify one of them, then pick the entire model to identify how many of such patterns are there. And in this one, it identified about 49 of such features and go and delete. It's as simple as that one. Let's take a look at this feature in this corner and recognize by the pattern. Now select the entire model to see how many of such patterns are there. And it did identify about 26 of such features and defeat. Likewise, we can also look at the traditional fillets in this model. For example, it is a small fillet. Identify one of them and select the entire model and see how many are there. And there are 42 such features and go defeat. So how quickly and how nicely and how elegantly then we can identify the features based on pattern and find how many of them are there in a selected geometry or a model and defeature that. Now, this model is just about ready to go for the next steps. Okay, let's see what's next. The new enhanced feature in Grizzly is tie connection. So this is something new and something unique in the industry, what we introduce in Apex. Typically, in any engineering models, when you would like to assemble the parts, what we used to do is to create a congruent mesh. In order to create a congruent mesh, we need to move all the bodies or all the parts into one part so that we can stick them together and mesh them and have a congruent mesh. What is the advantage and disadvantage of that situation? That once we stitch the parts, move all the parts into one, it becomes single monolithic structure. And once we do the baseline analysis, it's almost impossible or difficult to make any design changes because the original product structure is lost. Whereas in Grizzly, or even in Apex, when we introduced file connection, the idea behind this one is to create a congruent geometry and hence a congruent mesh, but yet maintain the product structure. So that whenever we would like to modify a design, we could take advantage of the direct modeling capabilities, and such as we can delete a part, delete a feature, and take a part and move it around and modify the design and continue to do the simulation with the original product structure. In the previous release, when we introduced tie connection, we used to do one tie at a time, whereas in Grizzly, now you can use a box pick and select all those and do tie all of them automatically. Let's take a look at that. All right. Here is the entire model, and let's take a look at the one of the main girders to which we have shown you how to defeature all those features, and then using the extend surface tool, we extended all those edges to touch each other. That's one of the requirements of a tie connection. We want to make sure all those edges are touching each other. Once we have done that one using our geometry tools that's available in Apex, we can go to page tie. And now, here also we have a tolerance. That means when we tie the edges, if there are any sliver edges that it gets created in the process of creating a tie, and it can clean up those extra slivers up to this given tolerance. And I gave a tolerance of 5 millimeters here because this model is huge. And this model is almost like 20 meters from here to here, right? Now we can select all the surfaces to be tied and with all the edges ready to be connected. That's it. We selected all the faces, selected all the edges, and the logic automatically detected and created a tie. In this one, this one is almost an edge-to-edge tie, and it's also edge-to-edge tie, whereas all the other things are edge-to-face tie. Those are the two techniques that what we have. We can create edge-to-edge tie or edge-to-face tie. And now we can quickly go and create a mesh, and let's use 50 millimeter element size to create a mesh after the tie, and this ensures the mesh congruency between the parts wherever it is tied. And quickly we can take a look at if there are any sliver elements we did create, or did it clean up all those sliver edges, and hence there are no invalid elements. As you can see here, this particular subassembly doesn't have any invalid elements. And now this is one congruent mesh geometry, yet it is multiple parts as the original product structure. Now this is ready for simulation. And I can get the other parts of the model here, show all. And now quickly, while I'm here, I'm going to mesh the other parts other sub-assemblies with the same element size. And we'll also go ahead and extract the thickness for all these parts. And this is one of the most powerful features of Grizzly, where we can extract the thicknesses from the original solids for the meshed bodies. While it is doing that one, let's go to what's next. We are also introducing what is called section view in Grizzly. Typically in a large structure like this one, where there are thousands of parts, and when we extract the thickness, possibly there could be one or two parts or one or two faces of a part is missing thickness, because sometimes the mesh model may be just outside the solid body where it might miss the thickness. There could be many other reasons why the algorithm may have failed in creating a thickness. And now, in the past, it was difficult to identify which part is missing thickness, and we have to navigate through the model browser with the thousands of sections to find one. But now in Grizzly, we're introducing what's called section view, and it's one more view in the model browser. And all the capabilities of model browser, such as show, hide, show all those things continue to work the way it does even in section view. And if there is a part that is missing the thickness, today in Grizzly, you can go to one of the parts that has a thickness assigned, and you can copy that one and reassign maybe to the adjacent part or wherever it is. Number two, it will show in the view that each of these parts or each of those sections, what is the thickness and what is the offset. And certainly there are thousands of properties are there in the model browser. Navigating that one is going to be unwieldy, and therefore we are also giving you the features such as you can organize those sections, by assembly, by part, so that it makes it a lot easier to navigate through the section view, and hence your model is ready for simulation. Let's go back and take a look at it. Okay, here we have created thicknesses for the entire model. And in Grizzly, I think even in the previous release that we had, you could visualize the thickness based on 3D. And if I set to 3D, toggle that, now you can take a look at the thicknesses based on 3D representation. Right now, if I overlay the solids, pretty much it is showing you all the thicknesses that is extracted from the solid. All right? So, where is the section view? In the model browser, if you toggle this one to section view, now it will give you what are the different sections it created in this model. Even for hundreds of parts, it kind of merged the equivalent thicknesses, and now we have about 13 section properties created, and its thicknesses and its offset. And if there are no sections that's created here, you open that one, and it will show you if there are any spaces that is missing thickness. And unfortunately, there are no faces in this model that's missing any thickness. If any faces were to be missing, then you would see the part that's missing thickness, and then you can go and navigate through here. And for example, I can take the thickness of this out of thickness 6, and when I click on that one, it takes you through the attributes panel, and now you can pick a space and you can assign the thickness. And also, when we switch this display, often sometimes it is to overlay the surface and the mesh. And now we also have a tool here which help you to change the graphics so that you can see it better. So it is that easy to now look at the section view, the missing sections. Unfortunately, there is no missing section in this model, and also all the other attributes of different properties of section view in the model browser. Okay, so what's next? So the new capability in FX is a scripting, and what you have been waiting for. And scripting is based on macro record. And anytime that you run a macro of any UI command in a Grizzly, it creates a macro of that, and it creates a Python. And now you can use the Python constructs such as data constructs, list, dictionary, looping, etc. to edit the Python, and you can create your own script. Secondly, sorry about that. Secondly, you can also access Python modules to access Excel spreadsheet. In most of the time that you would like to access the data, for example, in this satellite module which you are going to run, you would like to create a match, tie the parts together, and you would like to add some kind of point map at different locations, and also you would like to create constraints at different locations, and also you would like to assign thickness for different parts of this module. And all those data can be in a spreadsheet, and we can access that one through Python module, and then we can run the script so that it can automatically create a module, something like this, right? That's after you will create a macro record of the base geometry, and you can do the rest. And we are introducing the user-friendly documentation through Doxygen, and now this is very rich, and once you get to know how to access all these tools and the documentation, in my opinion, sky is the limit. You can make wonders by creating the scripts. Let's take a quick look at that one. Maybe we can run it here. Let's run the macro that was created for this satellite. And this macro was initiated by UI, and after that one, we access through Excel spreadsheet to complete the model. And once it is done, now we can set the context for running the simulation. And let's say, since buckling is a new one, let's see if I can set the buckling. And it says still missing loads because loads are not created in this model through the script. We can go ahead and add maybe a pressure load on the top here, for example, maybe 0.5 psi on the top surface here. That's it. Now we can run the buckling on this one. It's as simple as setting the buckling simulation in Apex, and which we have already seen the results exploration capabilities of buckling in the other example. So in this example, what is the takeaway? The scripting capabilities, reading information through CSV, and building a model and updating that model, which should be ready for running a simulation. And thanks to Larry, who gave this model and also the script, and he's one of the experts today in running the scripts in Grizzly. What's next? Connective forces. In any engineering simulation, what is important are two things, in my opinion: looking at the cross-section forces and looking at the connective forces. And once we are able to explore those forces in the connections in the model, and one can make an engineering judgment whether the fasteners in that model are adequate, the size and the shape of the model's fasteners are okay, it could be a bolt or it could be a weld, etc., and how we can quickly interrogate those results in Grizzly. In Grizzly, we need to do nothing. We can create the connectors like what we have the features in the previous releases of Apex, such as you can create a bushing, you can create a flexible link, you can create a glue, etc. And now for most of those connectors today, we support the connector forces. Probably still not available for the glue, but for other one-bit connectors, we should be able to take a look at the connector forces. Let's take a look at it. Okay. Let's bring in this geometry of hinge leg bracket and made out of many solid bodies. And let's run a script that is created for this. Connect to macro. And the script successfully created the model. Let's go and run the simulation to take a look at the connector forces. And so what did the script do basically? It did create text mesh for this left bracket, and it did create text mesh for the rest of the bracket, and it did constrain the certain areas here, and it did create the fastness between these parts. And macro record can create one of the fasteners, and then through CSV file, we can read in the connector locations and also the parts to be connected information. And now we can edit that macro and recreate the fasteners at all those fastener locations. Imagine if there is any model such as the ship hull or whatever, there could be thousands of connectors, right? And now using the scripting capabilities, one can create those kind of connectors. Let's take a look at how we can explore the results, how we can look at the connector forces in Grizzly. This is the typical stress plot for the lug load that is applied along the lug bracket, which makes sense. And I'm going to look at the contours on the uniform geometry. Now, where are the connector forces? Here, select all the connectors, or you can select even one connector at a time. And then connector forces. I'm going to hide the solid mesh. So what you are seeing here, the connector force. What do we have under visualization? When I toggle that from to scale factor to a uniform, now you can see the forces in each of those connectors. Now I can start animation of that one. When I click each of those connectors, now you see what are the connector forces. What other options do we have to explore the results of each of these connectors? Now you can look at the connectors arrow at the tip or arrow at the tail, because sometimes you want to see it better. Sorry. And the data visualization, and you can pass through different components of those connector forces. For example, X component, which is the axial force to the bolt, and Y and Z component, and maybe YZ component, which is the kind of shear component in the bolt. I can look at the axial component, and simultaneously I can look at the shear component. Now both are plotted here. I can look at that one and go back to visualization and show labels. Now when I box around, now you can see for that connector we have an axial force, which is in this case a tension in that bolt, and also a shear force in that bolt. And now if you like to, you can draw a box around all the connectors. You can look at the connector force. All right, once you look at this one, what other powerful things that we have in Grizzly? Let's say this one of these connectors is not adequate, or in that area that I would like to make some changes. For example, I would like to increase the diameter of that bolt, right? And what are the two things that one would do? I could go to the push-pull, in which I can select this bolt. Right now it is 3.18 radius. I'm going to make it as 4 millimeter. Now the diameter of this one increased. Now I can go to select that one and align this one. Now both the parts are aligned with respect to 4 millimeter. Now all the other things, that is connection and RB2, RB3, etc., representing the abstract representation of that board got updated. So once we modify the geometry, we could go to that particular connector, and in this case, connector number 3. Now, since we made the whole diameter as 8 millimeters, now we can go and modify the diameter of the bolt 8 millimeters. Now, pretty much, now you updated the geometry, updated the bolt, and now it's done. And what is next? You can check the context, run the simulation. Now we can take a look at what will be the connector forces after the design modification. So it is that easy and that innovative and that interactive to make any design changes looking at the section forces through any of these connectors in this example. What is next? All right. In FOSA, we have introduced the linear dynamics capabilities, particularly the frequency response analysis. And we have done quite a bit of enhancements to increase the capability of that simulation. What have we done in Grizzly? So most of the times, the input data that comes in as a time signal. And from the test data, when we get the time signal in the time domain, now in Grizzly, on the fly, to a50, we can convert that time signal into frequency signal. And once we convert that one, the rest is same as what we have done in FOSA. You can continue to run the simulation with a frequency response where the time signal has been converted. Right? It is that simple and that elegant. And all the other capabilities of exploring the results that what you have seen for the frequency response, all those things continue to be same. And you can take advantage of looking at the frequency response with time signal as the input. What is next? Analysis readiness and remedy. In previous releases of Apex, you have seen the power of analysis readiness. Be a novice engineer or be an expert. There is always a problem why a simulation failed, or what's the problem in my simulation model, why it did not go through. So, having known those kind of issues in the world of simulation, we have introduced what is called analysis readiness in Apex, meaning is the model ready to run? And if it is ready, if it is not ready, what did we have? It could identify the issue and it could notify the user where the problem is and what the problem was. In the previous releases of Apex, even though we knew the problem, even though it identifies and notifies, it was difficult to find where is that one and how to fix it. Whereas in Grizzly, now we have introduced what is called a companion tool within Apex so that it will navigate you to take to the location where the problem was and interactively you can fix that. For example, in this case, there was an invalid element that did not let you run the simulation. Now, it will take you directly to that location, and when you double-click on that one, it will show all possible scenarios that you can use to fix that one. So probably you can split the elements in this case, or you can move a node to fix that one. Okay? It is that easy and that simple and that navigation. And secondly, for example, what you're seeing here, let's say you have quite a few different materials that is defined in a model, and one of the materials has some missing properties. And it will take you through there, and double-clicking on that one, it will open up the material panel. Now you can edit that and correct the thickness and correct the property. So it is that innovative and that elegant. So you can not only identify and notify the problem, and Apex will also suggest what is the possible remedy to get over those kind of problems. That is the enhancements that what you have in Grizzly. What's next? In Grizzly, we are also introducing what is called MNF creation and export. In most of the vehicle dynamics simulation, often user would like to introduce flexibility into some parts of the structure. And doing that one today is quite a task, meaning you got to create a geometry, create a mesh, export the mesh, run that externally in NASTAN, after you identify all the interface points and etc., and then you can import that model neutral file into your Adam simulation. Whereas now in Grizzly, we will show you how elegantly and quickly you can create and export MNF so that you can take advantage of Adam's companion workflow between Grizzly and Adams. Okay. This one. Import geometry, in this case, a landing gear model. All right. So it has tons of parts in this assembly. Let's say I would like to convert this particular body into flex body, right? And take me to in the model browser where it is, and show only. And that made up two parts. Let's say I just would like to show on one of these parts. And quickly, you can go and mesh this part. And let's make it as maybe 25 millimeter element size. And hit mesh. Meshing is done. Now, we need to define what's called the interface point, where we are going to reduce the math representation of this model as a model neutral file so that you can take that one into World of Adams. And how do we do that one? And that's under attributes, what's called interface point, and how quickly we can create that one. As you can notice, the user experience we are trying to maintain very unique across the tools. In this case, we would like to create a model neutral file of this part and represent somewhere at the center between these two holes and in all degree of freedom. That's what is in place in this panel. And it could be a rigid body representation of that one. Okay, now you can select the inner surface of that one. And now you can put it anywhere to begin with. Okay, as you see, it is not aligned with respect to the axis of the hole. And how do you do that one? Let's say I would like to align this axis approximately aligned with respect to that one. Now it's aligned. Now I would like to bring that one to the center of this hole. You can select this curve. It brings a point at the center of the hole. Now that's at the center. Now I can say I would like to move to the center between the squares. Or I could potentially have a hard point that is defined here, which is most classic situation. Then once there is a hard point position there, I can pick this one and create the MNF distribution at that hard point location. It's as simple as that. And that is done. Now, how do we create an MNF? And basically, I can take that context, run the simulation, and now what it's saying, it is missing rows because we are not running static analysis. We are running normal modes on that part, and it's missing material. And let's go ahead and create a material. Right. Assign that material to this part. It is done. Now, under the settings, we go to the output request, and this is where MNF export is positioned to export, and toggle them on and identify where you would like to export this one. Maybe name of the MNF file. It is done. Now, let's run this one. So basically now you saw how quickly we can identify a part, mesh that part, create an interface point, Will it be a hard point location, or you can use your judgment where you would like to distribute that one and identify on the simulation. Pretty much it is done. Now, while you are here, you can explore to look at the behavior of that part and also look at it has created first 6 rigid bodies, and the first next mode is about 307 hertz, blah, blah, blah. And now all those things are exported into this abc.emitter. Now you're ready to take this one and go to your Adams companion simulation 2. Okay, what is next? So in Grizzly, you have seen quite a bit of rich capabilities of buckling simulation, X mesh, custom defeature, result exploration with cross-section forces, connector forces, and continued enhancements on existing tools such as the tie connections, macro record and replay, section view, and quite a bit of usability enhancements, for example, analysis, readiness, and remedy. All these things will help you to do a simulation on any complex structures like large fabricated structures. And with these capabilities, now we believe you can solve many engineering problems. And give it a try, certainly you will like it.